Today we're going over solving exponential and logarithmic equations. We're going to go over a few properties that you need to know before you start, and then some of the examples from the worksheet that you've been handed today. First, the difference between exponential and power functions. They can be often mistaken for one another. An exponential function has an x or its variable in the exponent position, whereas a power function has a constant in the exponent position. Exponential and logarithmic functions are inverses of each other, so we can use them to alter the positioning of that variable x. If you start with an exponential function, you can change it to log form by switching the input and the output. If you notice, the input for the exponential became like the y value for the log function, and we can do the same thing with log functions changing to exponential form. The inputs and outputs should switch places. This inverse relationship can also be seen graphically. Here in orange, I have an exponential function, which will have a y-intercept of 1. A log function has an x-intercept of 1, and they look like they are reflected across y equals x, as they should be for inverses. This is going to be important as we start to solve the equations. Exponentials cannot be equal to negative y values if you're looking at kind of a parent function exponential, not transformed. And log functions can't have inputs that are negative. It has no negative x values. But be careful, because transformations can change that fact. So really this is talking about that last step when you've reduced it down to a parent function. I'll show you a few examples as we go along. All right, so the first example we're going to do is example 1 on your worksheet. This section says to change the base to solve the equations. This is the optimal way to solve an exponential. It is much quicker, I think, than using logs, but if you don't remember how to do this later on, you can use logs to solve this, like we'll do in example 9. To change the base means that the bases on either side have something in common. They are equal to some number, the same number raised to a different power. So for example, I know that 32 is equal to 2 to the 5th. This is helpful because that means I can replace 32 with 2 to the 5th. And when the bases match, we know their exponents must match if they're equal. So I can kind of just ignore the base of 2 and solve using the exponents. So I can quickly see that x must be 2 for this problem. For example 4, that section says to solve log equations by changing to exponential form. So this is kind of using what we were talking about up here, the relationship between logs and exponentials. We're going to get that x out of the log by changing to exponential form. That's really the benefit to changing forms, is that you get to remove the x from whatever position it's in that might be hard to access. So the base is the same, 2, but the output from the log is now what the input is for the exponential, and what was inside the log goes outside. So I can very quickly see that x must be 32 in this case, and we're done. Okay, for example 9, which is a little further down, this one is also solving exponential equations. It is very similar to number 1, except as I start to get this base by itself, by dividing by 2, I can see that e, which is the base on the left side, definitely does not match or have any easy way to turn into 3 on the right side. There are some log properties you can use that can change those into the same base, and if you want to, you are free to do that. You'll get the same result. But for me, I like to go straight into changing to log form to get this x out of its exponent position. So for a log, this base is e. That is a natural log, or you could say log base e, either way. The output goes in, and the input goes out. All right, now to get x by itself, we just simply need to divide both sides by 3. And since your test is no calculator, this is where you would stop on your test or quizzes. If you want to have an actual number to plug back in and check your work, you should get 0.3662 approximately as your solution for this one. But I'm going to stop here and say this is pretty good because that's the kind of answer that you're going to be using going forward. On example 11, we have two different exponentials in the same equation, and that's really where this challenge comes in. If we were to just change this to log form, you're still going to have an x trapped inside the log, and that was the whole point of changing forms, was it wouldn't be trapped inside anymore. So there's another technique that we can use with logs, and that is to basically apply the log to both sides at the same time. So if I do that, I'll just get log of 2x minus 1 equal to log of 5 to the 2x plus 3. And the reason that is beneficial is that there's a log property that says that you can take exponents from the input and move them to the front. So I'm going to do that to get that x out of the exponent position. I'm using parentheses very carefully because that log is a number and it does get multiplied to the entire exponent. So that is a binomial. We have to distribute the log to those terms. Even if you divided by the log, you would still have to distribute on one of the sides. So I would just rather do it here and not create extra fractions along the way personally, but you are welcome to do anything that's algebraically valid. I'm going to distribute this log. Remember, it's just a number. It's an ugly decimal, but this is a much shorter way to write it than writing a long decimal. So it's x times that log minus 1 times that log, and then doing the same distribution on the other side. Now to get the x by itself, we're going to have to group it first. It says if you had two different terms with the x, we're going to group them and then factor the x out. So you can move it to either side. I'm going to move the x's to the left just out of habit. And now if we factor out the x, and keep in mind that logs are just numbers, the right-hand side's the same, we haven't changed it. Because this whole expression is really just a number, we're allowed to divide both sides by that coefficient. It's really just a coefficient in front of your x. So to get x alone, I'm going to divide both sides by that number. And again, if there's no simplifying you can do, you are allowed to stop right there. But again, if you're more comfortable with a decimal for now, you are allowed to plug that into the calculator. Make sure that you put parentheses around the top and around the bottom, otherwise it will not divide the way that you think it will, and you should get negative 2.1861 as your solution. Okay, our next example is number 17 on the back side. This guy definitely is exponential because we've got the x in the exponent position, but it looks a little funny. There's two exponentials and an extra constant, so it's like even more terms than the last example. For this one, I noticed that 9 and 3 have a close relationship with each other. 9 is equal to 3 squared. Cool, so that means there's a possibility I could substitute in a 3 squared in place of that 9, and we're going to go ahead and do that, because now at least these bases match, and that might be closer to helping us out. I also know an exponent property that when you have two powers on the same number, you can simplify it down to just multiplication. And multiplication is commutative. And then we can reverse that process again and get 3 to the x squared. These are equal to each other. Even though it seems weird that we can do that, it's because there's multiplication in the middle and multiplication is commutative. So I'm going to go ahead and rewrite that one more time. Now the reason I did that was because now we actually have something that's quadratic. There's a term that's squared, a term that's not squared, and then a constant. So I'm going to use u substitution just to make that quadratic factoring look a little more pleasant. If you can do this without the substitution, you are welcome to do that. U squared minus u minus 6 equals 0, and this is definitely factorable. So I can solve for my u's. And then don't forget to put the u back in, because we're not actually solving for u, we're solving for x. So 3 to the x equals 3, therefore x must be 1, and 3 to the x equals negative 2. But if you remember on the previous slide when we talked about these graphs, exponentials can't have a negative output. It's not possible. There is no x that you can plug in to get a negative 2. So therefore, this side just isn't true, and we're not going to get a solution from that half, and that's okay. The only solution is 1. The last problem I have is an extra practice problem from a different worksheet, so you don't have it on your paper as it is, but it's very similar to how you would solve numbers 20 and 22. For this, we are trying to change this into exponential form because we've got an x trapped inside of the log, but there's 2 logs. So again, I'm going to use some properties to combine those. That way we can change it into exponential. There is a log property that says that if you're adding 2 logs with the same base, you can multiply their inputs. So I'm going to do that very carefully with FOIL. Negative x squared plus x minus 2x plus 2. And now that it's a single log, it's basically like the problem number 4 that we did earlier, where you can just change it to exponential form. So base, power, inside. I'm going to go ahead and combine some terms while I'm at it. And now we can solve it like a regular old quadratic, which means quadratic formula, factoring, completing the square, whatever you feel like. I'm going to do factoring because those constants canceled, so this is a pretty simple factoring by GCF. And it looks like x is 0 and x is -1. Now here I want you to be very, very careful. Like I said earlier, logs do not allow negative inputs. And even though 0 is not a negative number, it's possible that depending on the transformations happening to the logs up here at the top, 0 could cause the number inside to be negative. Or a negative number like -1 could plug in and still be positive, and so it actually would be okay. The important part is to check that the input as a whole doesn't produce a negative number. So we're going to test our answers. You should always do this when you have a log as your input or as your original function, because you never know, positives can turn negative when you plug them in. So I'm just going to plug in my x values and check that those are positive inputs overall. The first one turns into a 2, the second one turns into a 1, so 0 is perfectly fine, it's not causing any issues. When I go to plug in -1 into the originals, whoops, that's a +1 over here, minus -1. Those also are both positive. We've got 1 and 2. So even though x is a negative number, it doesn't cause any issues because of the transformations that are happening to those logs. All right, that's everything. Your assignment for tonight is 3 and the even numbers from 6 to 22. If you want to complete the entire worksheet, you can get an extra participation sticker for this 6 weeks. Since I'm not here today, we can't do any participation in class. I want to give you that extra chance. Thank you.